안녕하세요. 어서 오세요. 잘 지내세요. Now here we have a Beckhoff servo drive, and this model number is AX2003. And we're going to test it. And I don't have the servo motor. It's kind of funny because I'll have the drive and no motor. I'll have the motor and no drive. And when I do have the motor and the drive at the same time, I don't have the cables between them. So what we're going to do is I'm using the light bulb bank there to simulate the motor, connected to U, V, and W, output to the motor of the drive. And here I have a resolver which I mounted on a DC motor. And in the olden days, when I first started testing servo motors, I'd rotate that resolver by hand to allow us to ping through the light bulbs of the output when the drive was enabled. But I got smart one day and I said, you know what? If I mounted this resolver on a DC motor, I could have the DC motor rotate the resolver for me. So that's what this is right here. If it looks a little odd, yes it is. Okay, one problem with this setup here and this drive is that since I don't have the actual motor to run on this drive, to test this drive with, we are going to get an F12 alarm after a few moments of runtime. And the F12 alarm is a motor phase error. Of course, light bulbs are not the motor, so we're going to get that F12 alarm. I'll read the actual alarm from the PDF, but it has to do with the motor phase. We have 24 volts from this power supply down here, which is powering up the control voltage to the drive. This 24 volt power supply right here is going to provide the I/O voltage for this connector right here so that we can enable it and also jump out the positive limit switch and the negative limit switch. This power supply up here is going to run the DC motor and rotate that resolver. Now here we have our line input, and according to the drive label right here, it says input 3 times 230, that's 3 phase 230, or 3 phase 480. And I'm going to use 220 volts AC 3 phase for the line input. I always like to use the lower voltage for no particular reason, except I'd rather get shocked on 230 than 480. And it's not going to make no difference whether this drive blows up on 480 or blows up on 230. That's not going to matter. Either one of those voltages, when they go south, they destroy things indiscriminately. Okay. Now I have this laptop over here. We'll get closer to it when we go to communicate to that drive, but that's only for transferring parameters and setting up the drive. But I'll show you how to do that. That's another aside. We don't need it to test the servo drive. It's just to when you're putting parameters into it or drawing parameters out or setting motor type and whatnot. We'll go in there and I'll show that to you in case you ever need to do that. So let's get started. All right, I'm going to turn on the control voltage, and we'll get closer to this display right here in a little bit. You get to see how it boots up. I like to bring it all the way up to where it says 03 in the display. We have 03 in the display. I'm going to apply the 220 volts AC three-phase to the drive. And now it says P03 in the display. P meaning that we have the line voltage applied to the drive. And when the line voltage is applied to the drive, you can hear a relay click in here, and I believe that's for the pre-charge circuitry, the pre-charge relay. Now I'm going to enable the drive to run. Let's get that DC motor going here real quick. All right, we're rotating. Now I'm going to enable the drive. And I'll put the hookups here at the end of the video. And we're running. And there's our P12 alarm. And because that's a fatal alarm, the output to the motor has stopped. F12, I'm sorry, I said P12, didn't I? I meant F12. So let's cycle power here to reset the drive, and we'll run it again. We slow that motor down a little bit. Slow it down a little bit more so we can see. All right. There we go. We have P03 in the display. We're going to run again, enabling the drive to run. There we go. Okay. And we have F12 in the display again, indicating that we have an alarm. F12. That's the problem with testing this drive with this setup right here, is that we get that alarm. Can't be helped, but we do get to see it run for a few moments. I want to back the camera up so you can see the UV and W portrayed on our light bulb bank. Cycle power here. We're going to enable the drive to run. Ain't that pretty? Now if this was an actual motor, it would be rotating. There we go. F12 alarm. F12, according to the PDF, is motor phase alarm. Motor phase missing, cable break or similar. That's the F12 alarm. We will always get that when we run that drive in this configuration. Now if we had the actual motor and the closed loop, the proper closed loop, we would be running right now. We would not have that fault. Let's get close to the display and you can see how this drive boots up. All right, let's apply 24 volts DC to the control voltage. Let me push this in a little bit because it's a little bit fuzzy. There we go. 5.56. There we go. P03. Now if you don't have the line voltage applied, it just says 03. We're going to enable the drive to run. There we go, we're running. And we get the F12 alarm. And the motor has stopped running. Show you a couple other alarms we might get. Okay, let me cycle power to reset that fault. .56. There's P03 again. I'm going to turn off the external voltage, the external 24 voltage, to the I/O. There's N10 and N11. P03, N10, N11. N10 and N11, that's our positive and negative limit switch inputs. That means they've been disconnected from the 24 volts DC. Let me turn that back on. There we go. Applied the 24 volts DC to the I/O connector. Now I'm going to disconnect the resolver and the motor thermal. We'll see what alarms we get. Come on. There we go. What did we get? F04 and F06. Let's see what those alarms are. F04 is the feedback alarm. Cable break, short circuit, short to ground on the resolver input connector. F06 is motor temperature. Motor temperature too high or temperature sensor defective. Limit is set by manufacturer to 145 degrees Celsius. Let me turn that control voltage off. There we go. That's the test of the servo drive. AX2003. Now let's look at the program that you can use to communicate to this drive. This program is named drive.exe. We'll go up here to the COM1 button, press that, and the program has pulled in the parameters from the drive. You see there's a lot going on here, but you can get around in here pretty good. I'll get up here so I can show you a few things. Here's the motor type, AKM51G. It's resolver feedback. Here's the digital I/O. Here's the analog I/O. You can click on those and see what's going on. Here's the digital I/O. Our P-stop and N-stop inputs have 24 volts applied. They're both high right now. And if we pull the enable high, this point right here will go and show a high. Let's enable that. There we go, we're enabled. The enable input goes high. Let's back up here. We'll go back to the main page. Let's go look at the analog input. Here's the analog input. Now I don't have an analog input applied to this drive, but it shows you a couple of the inputs right here. Let's go back out to the main page. Let's see, we have three types of ways we could set this drive up: speed control, position control, or torque control. And right now it's set to speed control. Well, there you go. It's an interesting little program. Drive.exe. Now at the end of the video, when I get to the house, I'll show you my hookups so you can test your Beckhoff servo drive, model AX2003. Thanks all for coming by and seeing what we're doing next. We'll see you when we get to the house. Thanks for coming over. 대단히 감사합니다. 안녕히 가세요. Let's take a look at the hookups. Now, here's analog input 1. There's 2 analog inputs to this drive, and this is one input right here on 4 and 5. Now, I didn't have an analog input going to this drive when I was testing it. Whenever I run the resolver into the drive, the rotating resolver, it will fire the outputs when I enable that drive to run. So I did not have to have an analog input. But if you have the actual motor that runs on this drive and the resolver feedback and UV and W connected to that motor, you have to have an analog input. So here, we'll take a look at how to hook up your analog input. Pin 1 is analog ground, as well as pin 10 is analog ground. But pin 1 is closest to 4 and 5. Analog in 1 plus is on 4. Analog in minus 1 is on pin 5. Now I took pin 4 up to pin 1, connected them together, and then run that over to an external power supply's ground, whose output is plus or minus 10 volts going to the wings of this potentiometer, whose wiper is going to pin 5. And when you adjust this wiper either more plus or more minus, the motor will go either clockwise or counterclockwise, and that's your analog input. Now, analog input 2 is on pins 6 and 7. These 2 pins right here, 6 and 7. It appears you can have, and I won't be able to prove this, but it appears you can have 2 analog inputs. And they are possibly, I'm not sure, but they're possibly summed together to provide the analog input to that drive. Now let's go down and look at the digital inputs. Here are the digital inputs that I use to run that Beckhoff Servo drive AX2003. On pin 13, that's your P-stop. That would be your positive limit switch input. On 14, that's your end stop. That'd be your negative limit switch input to the drive. I tied both those to plus 24 volts DC from this second power supply. The enable is on pin 15. When I connect the enable to plus 24 volts DC, that enables that drive to run. Down here, the ground of the power supply going to pin 18. Very simple hookups, not much to it. Let's go look at this connection down here. And this powers up the control. This is the X4 connector. On pin 1 and 2, you apply plus 24 volts DC from an external power supply, and its ground to pins 3 and 4. 1 and 2 are tied together internally in the drive, and 3 and 4 are tied internally together in the drive. So you only have to run either 1 and 3, 1 plus 24, 3 ground. And that will power up the control. Next is the power connections. Here are the power connections. Now L1, L2, and L3 and protective earth are on the XOA and the XOB connector. These connectors are in parallel. I applied 220 volts AC 3-phase to L1, L2, and L3, and that brought up the DC bus for the IGBT to run that motor. Here on connector X7, you can actually, after you get drive high voltage applied, you can measure the DC bus. Plus DC is on pins 1 and 3, and bus ground minus DC is on pins 2 and 4 of the X7 connector. Here on X8, we have our regenerative braking resistor connections. On pin 1, that's labeled minus RB. That goes to the collector of the internal IGBT that pulse width modulates that regenerative braking resistor. And most of the time, when you get these drives into your shop, pins 1 and 2 will be jumped together. That allows for the use of the internal regenerative braking resistor that measures about 67 ohms thereabouts. It's a power resistor inside the drive. Plus RB external, if you wanted to use an external IGBT, if you wanted to use an external regenerative braking resistor, you would connect one side of it to pin 3 and the other side to the collector of the IGBT on pin 1. Pin 4 is minus DC. That's your DC bus ground. Same connection as pin 4 on the X7 connector. The X9 connector, motor / brake. Now I've never connected pins 1 and 2, and I'm not sure, but I'm guessing that is an output to release electromechanical brake inside the motor. I'll have to look that up in the future. Or y'all can look it up in the future and let me know in the comments what pin 1 brake minus and pin 2 brake plus do. Pin 3 is your protective earth again. And pin 4, 5, and 6, this is the output to the motor. 4 being U, 5 being V, and 6 being W. This is where I connected the light bulb bank to simulate the windings of the motor. If you had the actual motor, this is where you would connect your U, V, and W of the motor to the drive. That's the power connections. Let's go look at the resolver. The resolver connections, very important to the operation of this servo drive. It's on the X2 connector. That is a DB9 connector. It is a female connector on the drive. Pin 8 is your cosine input, pin 8 and pin 4. Pin 8 is S1, pin 4 is S3. That's your cosine connections. Pin 7 and 3. Pin 7 is S2, pin 3 is S4. That's your sine connections. Pin 9 and pin 5. That's your excitation waveform that drives the rotating transformer of that resolver. 6 and 2 are your motor thermal, and I jumped those out on the connector to clear the thermal alarm. Pin 1 is your shield of the cable. You connect that to pin 1. That's your resolver connections on X2. The communications, so that you can look at the parameters of the drive or upload or download parameters from and to the drive. That's on the X6 DB9 connector. Let's go look at that real quick. Now I used a RS232 cable, and pin 2 is your receive data, pin 3 is your transmit data, and this is on the X6 connector, and it serves a dual purpose. it's either a PC interface or a CAN interface. Pin 5 is ground. For the CAN communications, pin 6 is CAN low, and pin 9 is CAN high, if you wanted a CAN bus interface. But we used the RS-232 interface on 2, 3, and 5 being ground. Is that everything? I think so. Let's go look at my little bit of drawings of that regenerative braking circuit. I don't have the gate circuit mapped out. If y'all wanted to do that sometime in the future, you could, but this is the connections to the X8 connector. Let me write that in there. X. Come on, pen. My pen's not cooperating. Let me get another one. X8. I'm upside down. So here's the collector of the IGBT, and its part number is BUP314. Its collector goes to pin 1, labeled -RB. The internal regenerative braking resistor, one side goes to the plus bus, that's your DC bus, and the other side of the resistor goes to pin 2 of the X8 connector, labeled +RB internal. Now for an external braking resistor, you would connect the one side to pin 3, that's plus bus again, plus DC, and it's labeled +R external. And then you would take the other side of the external resistor to pin 1, -RB. But most of the time, pin 1 will be jumped to pin 2 so that you use the internal braking resistor. Pin 4 is DC bus ground, -DC. And you can see the emitter of the IGBT goes to bus ground, so that when this is pulse width modulated, then the energy from the servo motor being stopped, it dumps its energy back on the DC bus. This is the purpose of this circuit right here. When you rapidly stop a servo motor, that energy is placed back on the DC bus. And if you don't have a way to dissipate that energy, you can damage that drive. You can cause overvoltage damage on those bus capacitors and the three-phase bridge and possibly the IGBT. So you take that excess energy that's placed back in the drive from the motor being rapidly stopped, or a high inertia load on that motor causing it to suddenly stop. That energy is dissipated into the atmosphere through heat of this, the heating action of this 6-7 ohm resistor right here. So it's pulse width modulated to ground through the IGBT. Did I explain that correctly? It sounded right in my head, but anyways, you get the idea. The excess energy dumped back in the drive from the motor being stopped is dissipated into the atmosphere as heat through this resistor right here, being pulse width modulated to ground through the IGBT. There, that sounded better. Okay, I think that's everything. I think that's everything. Y'all have you a good day. And when I get to the house, I'll put all this together and put it up on the internet, and y'all can see ways of testing your servo drives, the Beckhoff AX2003. If you're lucky enough to have the motor and the cables and the drive all in one place, that would be really nice. If you do, put you a video up there. I'd like to see that. Thanks all. Thanks for coming by and supporting my channel by viewing the videos and whatnot. It means a lot to me. It means a lot. Thanks again, and we'll see you in the next one.